because we have the KR going on, 3 over KR cubed minus 1 over KR times the sine of KR minus 3 over KR squared times the cosine of KR, like this. Turn the air conditioner on. There's over 2,000 watts of light in this room, and it gets a little bit warm. Okay, so where okay. Okay, so these are the, depending on how much work you want to do, these are your Bessel functions, okay? That are solutions to that differential equation from previous. Now, you need to, these are solutions, these are the wave functions, okay? These are like the higher order terms you've used, like this is going to be more accurate of a description than this description here, right? But we need to take the complex conjugate and plot that, which is just the absolute square, is another way of saying it. And because there's no imaginary parts in these guys, it's easy. So you just square this whole thing and plot that. But hold on, we've got to do a change of coordinates first. Okay. Because if we draw and we have a slit here and a slit here, right? Let's see if I can get this darker. Okay. All right, and about right there. So this slit's here and this slit here. Okay, and we let this be a distance y away. Now this is different from my notes too, but the reason I'm letting it y is because, I tell you what, let this be L. That's easier, all right? And then let this distance here away be x, like this, all right? Okay, so we're gonna let this be our origin right here in between. And from here to here, the distance from here to here, this distance here, that distance will be equal to, or what we're going to let our, let's see how I did my coordinate system. I want to match this because this is the easiest way. Yeah, D. Let this be D. Right? Like that. Okay, then look. If this wavefront is being originated from here, right, then that wavefront is going to be the triangle corresponding to that will be this triangle here. I drew that a little off. So let's start from here. Okay. Now, if this is L, the length of this side is L, right? What is this length right here? From here to here. Well, it's X minus D, right? So this is X minus D. Like that. Okay? And so if we do the, L squared plus X minus D squared equals C squared, then this over here is going to be equal to the square root of L squared plus X minus D squared. And that is R. R1. Okay? So this is what you replace R with in the equations, right? To solve this problem. Now we're going to do it, so don't worry. But basically we've solved the problem. Now, okay, so K here, right? Okay, so let's just do that. The energy that Davison and Germer used the first time this was first ever done, they used 54 volts. Okay, so each electron had an energy of 54 electron volts. Okay, but we need to convert that to joules to plug in, okay, because we're using H bar in our equation, which is in terms of joules, and you could use it in terms of EV if you wanted, right? But if you let the energy, I'm just write this down, let the energy of each electron be equal to 54 EV, and then lambda is equal to 1.67 angstroms, so 1.67 times 10 to the minus 10 meters. And then D is just equal to lambda over 2. All right, so there's some physics right there. I'll explain in just 1 second. 0.835 times 10 to the minus 10. Meters. Okay. Now why is D equal to lambda over 2? In order for interference to occur between two sources, the distance between the two slits, right, which we see is 2D, right? Well, the distance between, from here to here, here's a good way of annotating this. From here to here, this has to be about lambda, right? Okay, so we see how one of these, this is half of this, right? And so that's why I put this here. Because in order for interference to occur, this condition has been observed to be true. Okay. All right, so 0.835. Now, 54 electron volts, here's, the creative process at work. I want to convert this to joules for you, because if you're going to plug it in your calculator, you need to put it in joules. So let me go grab a calculator. Okay, got it. Multiply times the charge of an electron, basically, and you'll get, and yeah, you know what? A convenient way to convert this, I always have to think about it, okay, 1 eV. 1 eV is equal to 1.602 times 10 to the minus 19 joules is the conversion factor. But look, 54 eV, just turn the E into the charge, and this is what it is. It's 54 times 1.602. Learn something new every day. Well, this is just a convenient way to convert this. And that would be in volts. And that comes out to be 8.65. 8.651 if you want to be piggy, times 10 to the minus 19. 10 to the minus 18, sorry. Joules. Okay? All right, so then K is equal to 3.765 times 10 to the 10. And the units are, whatever the units are for K. Let's see, what's the units of a wave number? I believe the units of a wave number 1 over a meter, I think. But whatever, this is the number, okay? And this wavelength was calculated in previous, in Schrodinger's quantum mechanics. Part 3 is the current, description name in the tutorial. This was calculated using the energy, right? We did all that already. Okay, so this is what K is equal to. So let's just, for the sake of this tutorial, I'll let you do the first order and the second order for fun. Let's do the zeroth order solution to this problem, because I know it gives us a nice, it gives a nice graph because I've done it. So I haven't plotted these guys yet. So something for all of us to share in, I suppose. Okay. Now, here's the thing. Okay, so psi 0, and we've got slit 1 here. We'll call it slit 1, and then we've got slit 2, don't we? And let's do this. I always like A and B better for some reason. Let's keep it consistent with the previous tutorials anyway. A and slit B. Okay, so psi A. Oh, and taking the complex conjugate, by the way. Okay. All right. Again, part of the creative process. God, I hate this. Taking the complex conjugate, you need to